So in last video, we explained that theorem 2.1, we want to prove the angle alpha, which is formed between the straight line, the tangent, and the secant, is half of the measure of the central angle. The central angle is also considered, the measure of the central angle is also considered as the measure of the intercepted arc PQ. And also we need to prove the bigger one, SPQ, is also half of the major arc PQ. We're gonna prove the first one by this table because it's kind of easier, very clear to use the table here. We can also use sentences if you want. You can say since the measure is this, then we have since t is perpendicular, instead of using tables. Here we have statements. First statement I have is the measure of OPQ is, so the measure OPQ is equal to 90 degrees minus alpha. So because we notice this is a triangle, OPQ is a triangle. So first I found out this angle OPQ, that's 90 degrees minus alpha. The reason is t is perpendicular to OP. That's the definition of tangent to a circle. If we have a tangent, the point P, the tangent at point P, and the center O, this radius is perpendicular to the tangent. So that's just definition. So if it's a tangent, of course, the angle is 90 degrees. OPQ is 90 degrees. So I should say this angle OPT. Well, this is looks like use the same letter. It should be a different letter here. So OPT is 90 degrees. OPQ is 90 minus alpha. And because this is isosceles triangle, it's a very good property we can use in when we have a triangle through the center, because OP is a radius, OQ is a radius, and OP must be congruent to OQ. That means this angle, two base angles OPQ and OQP, they're congruent. So if this is 90 degrees minus alpha, then this must be also 90 degrees minus alpha. And the central angle is beta. So in this triangle, we add these three angles, we should get 180 degrees. This is what we have proved before. The degree sign in any triangle is always 180 degrees. So 90 degree minus alpha plus 90 degree minus alpha plus beta is 180 degrees. Now we can simplify this, combine like terms on the left side. 90 plus 90 is 180, cancel the 180 on the right side. And we add alpha and then add another alpha, when we get 2 alpha on the right side, and divide by 2, so we get alpha is half of beta. So this is just by the simplification of this expression. And so from this we can prove alpha is half of beta. So in this case we use the two things, the definition of a tangent to a circle. So this, we must get a 90 degree angle here. And we also use the degree sign in the triangle, because we want to find the connections between alpha and beta. And the connection is this triangle, the degree sum. Okay, now we have to prove the other angle, because SPQ, if we look at the angle SPQ and the angle alpha, because they form a linear pair. We have talked about the linear pair in chapter 1, the first class. We know they must add up to 180 degrees. So this is straight line. So if this angle is alpha, of course SPQ is 100 degrees minus alpha, and it's also equal to 100 degrees minus half of beta, because we just proved from part 1 alpha is half of beta, and we can factor out 1/2. So that's equal to 360 minus beta. This can be verified if I distribute 1/2 by distributive property. 1/2 times 360, that's 180, and 1/2 times beta is minus 1/2 beta. So that's how we get this. Factor out 1/2, we get 1/2 times 360 minus beta, and that's the measure of the big angle SPQ. Now we want to prove this angle is half of the major arc PQ. So again, by the definition of a measure of major arc, if you want to go back to a few slides before, the measure of a major arc is 360 minus the measure of the central angle. So we go back here, come back here, we have the measure of this major arc will be 360 minus the central angle beta. Okay, so we have two things we want. The left side, which is the measure of SPQ, the angle SPQ, and the right side is the measure of the major arc PQ, which is 360 minus beta. So clearly we can see 1/2 of 360 minus beta is exactly half of 360 minus beta. So we proved the second part. Okay, so the proof is, we first prove the measure, this measure is half of 360 minus beta, and then we use the definition, this is 360 minus beta. So that's the 1/2 relation between them. Okay, so that's the proof of 2.1. And the next we're going to use the theorem 2.1 to solve this problem 2.1. The picture in the textbook, there it has a picture which is probably better than my picture here on page 80. If you can open your textbook and look at page 80, figure 2.9. First we look at the problem. We want to find the relation between the measure of the inscribed angle. So what is the inscribed angle? We talk about the central angle. What's the central angle? The central angle is must pass through the vertex is at the center, so that's why I call it central angle. Inscribed, the center, the vertex is not at the center, it's on one of the point. So it's an angle whose vertex is on the circle and whose sides are the chords. So if you look at it here, this angle between chords AP and BP. P is not the center, P is a point on the circle. So this angle is called APB. Here is called the inscribed angle. And if I connect OA and OB, I get AOB, that's the central angle. And we want to prove this inscribed angle, the measure of this inscribed angle, and the measure of the intercepted arc, which is this arc AB. We want to find a relationship between them. So what we do is first we construct a tangent line PQ, a tangent PQ to the circle O. And now we have two angles. So because we have two chords, we use the tangent line, tangent PQ, and the chord AP. So kind of forget about the chord BP for a second. So the angle between them, formed by them, should be half of this arc AP. So this is theorem 2.1 we just proved. So that's the second statement here. Angle QPA, this angle formed by the tangent and the chord PA, is half of the measure PA, or I can say AP. Similarly, if we consider the tangent PQ and the chord PB, so forget about the chord AP, we have an angle QPB, and the arc between them is arc PB. And by theorem 2.1 again, the measure of this angle is half of the measure of the arc. Now we want to look at this angle here, APB. From the picture we can see, or it's better to look at the picture in the textbook on figure 2.9 on page 90. So the bigger angle formed by tangent and the PB minus the small angle formed by the tangent and the PA, we get exactly APB. That's the inscribed angle. So we subtract the first two equations, the bottom one from the top one, we get angle APB, which is equal to half of measure of arc BP minus the measure of arc AP. And so if you look at the picture, what is the measure of BP? So BP is from here to here minus AP is from here to here. We get exactly AB. So the measure of this part here, measure of BP minus measure of AP is equal to measure of AB. So that's how we get the inscribed angle. What's the measure of inscribed angle? It's half of the measure of the arc. And the next theorem 2.2, is based on the problem 2.1, the inscribed angle theorem. So now the measure of inscribed angle equals half the measure of the intercepted arc. So this is the inscribed angle alpha here, and the O right here is the central angle, and the arc BC. We want to prove the inscribed angle alpha is half of the measure of BC. This is what we have just proved, basically. So if you look at the picture here, we proved the inscribed angle is half of the arc AB. So it's just a different picture. And the corresponding corollary, in any circle, all of the inscribed angles intercepted the same arc are congruent. So this is a very useful corollary. If I draw two different, first of all, suppose we pick 2 points, x and y here, and we pick another point A, and we connect XA and YA, so we get an inscribed angle. And then we pick another point B on the circle, we connect XB and YB, then we get another inscribed angle. So we have two inscribed angles here at A and at B. What's the relation between these two inscribed angles? And it's very easy to see these two angles should be congruent. Why? By 2.2, theorem 2.2, the inscribed angle theorem, the inscribed angle is always half of the arc, half of the measure of the intercepted arc xy. So angle A is half of the measure of xy, and also by 2.2 again, angle B is half of the measure of xy. If both of them are half of a measure of xy, of course, angle A and angle B are congruent. In fact, similarly, if we consider the angle x and angle y, they are also congruent because they are both inscribed angles, and also the intercepted arc of x of this angle AXB is arc AB. So x is half of AB, and similarly y is half of AB. So x and y should be equal. And so this theorem, inscribed angle theorem, and the corollary are both very useful.